So it's basically about how RightScale architects their own databases, our own databases, and for HA, for DR purposes, scale and stuff. So what's in the menu for today is basically some intro, some level setting stuff, some light data taxonomy appetizers type of thing, and then we're going to get to the meaty first course about how we actually put this together. I want to make sure that we understand what this talk is. This is about how we architect our database systems. It's not about our overall architecture. It's not about data modeling. It's just like taking a few representative systems that we have and showing how we have deployed it, the rationale behind it, or as much rationale I can give you with 35 minutes. Okay, most of it is in production. There's a couple of the things, the more advanced things at the end that we're still working on, right? But otherwise, everything else is available. Now, before getting into the meat of it, what I want to do is, spoil a little bit some of the, the tension that might come in from the point of view that, saying right away that we use a mix of relational and non-relational databases, in particular MySQL and Cassandra, right? And some S3, but S3 is less interesting in terms of lots of things that you can do. Okay, it's mostly for backups and archiving. So because we're going to talk about those things, I want to talk about 3 areas in terms of differentiators between MySQL and Cassandra, right? So that at the very least, it's going to be a fast thing, but at the very least, we're going to be in the same level. So number 1 is transactionality. Obviously, MySQL is a very strong, has very strong ACID properties, and that's why we like it, all of us. And Cassandra, on the other hand, is a very distributed architecture in which there's no consistency, it's eventually consistent, there's no isolation almost, no atomicity, and obviously it is durable, okay? But so we're used to these good properties. We have to live without those properties when we go to a NoSQL database. I know that I may preach into the choir, some of you guys that already have it, but it's a good level setting slide. In terms of availability, though, this kind of goes the other way. MySQL is really not very highly available, right? You can use replication, you can use all kinds of things, but at the end of the day, there's glitches, right? You could make it very fast, but it's not highly available, okay? And you probably don't want to go into the master business, otherwise you really know what you're doing and your data model allows it. Cassandra, on the other hand, that's where it shines. It's fully distributed, there is no master, there's replication all over the place, and there's sharding, and you can do sharding across multiple data centers, okay? So it's really good from that perspective. In terms of sharding itself, as I said, Cassandra does shard internally their data. MySQL also doesn't have anything in particular inter-node, right? Inside a node, MySQL has a lot of optimizations about how to place the data, but across nodes, there's nothing there. So those are kind of the tools that we have in the tool set. All right, let's start with the taxonomy. So I picked a few systems that we have internally because they have specific semantics that I think are interesting to explain in this talk. By no means this is all the systems that we have. Okay, so let's start with the first one. First one is global objects. You probably can identify that in your applications. Every application has global objects, things that are that are common across whatever the tenancy model that you have, right? In our case, things across accounts, users, that a user can be connected to many accounts, the plans, obviously everybody sees the same plans, settings, et cetera, et cetera. Part of that is also the multi-cloud marketplace, where the library, maybe if you guys are used to, like going, browsing, what templates exist, you can import them and stuff. That's also global, right? Everybody sees that. Another part of data that we have is the most common data that you're used to dealing with, things in the dashboard, right? Through user in the dashboard or through the API. It's like your deployments, your inputs, your alert specs, any template that you import, all that is something that is private to your account and it basically belongs to this category. I pointed three of the internal services that we have because we'll see that these 3 have interesting semantics and data that changes how we have implemented the storage for them. But we'll see that later. Another piece of data that we have is something that has to do with polling the cloud for state changes. We need to constantly poll the cloud for what's happening and then send messages back to the core such that we know, that things are happening, right? That is also private to the account, but it's more of a cache, right, of what we've seen in the cloud in the past. We also have a lot of routing data, such that instances can talk to other instances or run scripts in other instances, or and do this type of operations. So it's kind of the data here is more of a registry. Where are the agents and how do I get to them? And finally, something like painfully obvious to everybody, because we have monitoring and syslog collection of data, right? We have to collect data and store it somewhere. Okay, now these are a small set of representative systems, something that I wanted to do before starting to get into the data architecture is that there's a couple interesting slices, a couple interesting things that we can do with these systems. Number one is to see who is accessing this data. If you think about it, everything that I described falls into two categories. Data that basically users want through the API or through the dashboard, right? Their objects, their audits, browsing, the marketplace. And data that is really, it's about the instances need, or that is really related to the instances. So there's user access and instance access. And what that can help us do is placement. So if we know that this is used by users, we could have all this data somehow push it closer to them, right? Much better. And same thing here. If we have the instances requiring this data, we want to push that data back to the instances, very close to them. So another way that you can slice this is about the globality or the scope of the data. Some of this data is global, right? Like I talked about, the assets of the marketplace, the plans, the users, but most of this data is account related, right? They belong to an account. So also that can help us from the point of view of knowing how we can shard our system. Global things are difficult to shard. Account related things are a little easier to shard. Okay? So if we if you superimpose these two scenarios, we can see that we come up with three categories. Data close to the user, but that has to be accessible to every user. Close to the user, but it's really account specific. And then close to the cloud, and is also account specific. So we don't have the fourth category that would be close to the cloud and global. Because inherently, if it's close to the cloud, it still relates to one of the accounts. You cannot have one instance of one account talk to an instance of another account, so to speak, right? That's why it's not there. We'll see that the routing data, though, has some semantics that has some global feel to it. So in a way, you can put some of the routing data into that fourth category. All right, so let's get to it. So I've divided this into the four quadrants of these four categories. So I'm going to start building the system as they belong here in their category. The first thing is the global data. The global systems, not one, but many, that we have are mostly implemented with mySQL. That's because there's a lot of asset semantics that we need there. It's very transactional. Publishing templates, users, having settings. It's very, very typical to what you do with a mySQL relational database. So we heavily use master-slave replication for these systems. And the interesting point there is that the availability of these global systems is not that important. And I'll tell you why. Because most of these things at the right level, it's okay if if we at RightScale cannot add a new plan today, right? If we have to wait 5 minutes because something went down, it's okay. If you cannot browse the library for a couple minutes, that's probably okay. Right? That doesn't mean that we cannot make it much more highly available, but it's definitely something that is not as highly available as some of the other systems. There's an interesting part here, though, that must be highly available, and that is the read of the global settings. So while I don't need to be able to create a user at any point in time, I need to know that this user belongs to this account. So me reading that information, that is very important. That's why we actually have custom replication. We provision this data to the rest of the system such that these other systems have it locally for read-only. They cannot change it, but they can always read it, right? So we massively replicate that data. We do this through a custom replication. We don't use mySQL replication for a variety of reasons, mostly because we need more control. We have several sources that we have to replicate into one. mySQL does not support that, per se. So we do it at the application level, in which we can actually do interesting resync algorithms. Because when you have a master, multi-masters, replicating to this new node, and something fails, then you don't know what data you have. right? Because you're mixing two streams, so how can you make sure that you're in sync with your sources? So since mySQL does not support that, we do it at the app level. Okay, so that was the global piece. The next piece is user data, but it's account related. And I have 4 representative systems here. The bubble there with the dash is to represent most of the dashboard or API features that you see. Okay? That is still really, really relational, and we use mySQL. Right? You have a deployment that has a set of servers. You have a server that has a set of alerts. So that's very relational in many ways. So we heavily use master-slave replication, many slaves, and we actually read from the slaves whenever we can, when you need a very high read throughput. But the interesting thing here is that every single row that is in all these databases over here in the dashboard is tagged with an account ID. So for every piece of data that we have in these databases, we know which account ID belongs to. We don't need, we could do the same thing by doing joins to the account, but we don't do that. That way, we can very easily see which parts of the data that we have belong to A, or which parts of the data belong to B. We can even extract them if we want them, right? So we've been very careful about that since the beginning in having that data model. Now, there's a lot of other systems in this category that are not using mySQL. In this case, we're using Cassandra. So, for example, so I have 3 examples, but in general, we started using Cassandra when we can dumb down the data model, because designing data models for non-relational databases is kind of interesting, because you kind of have to know exactly what the patterns of access is. Not like mySQL that you put tables and then you can relate them to however you want by creating indices. It's a bit more denormalized, it's a bit more involved. So it's easier when you can dumb it down to a easier data model. So whenever we need a lot of scalability, we have used Cassandra. So the tags subsystem is a good example of that, I think. So the tags, subsystem is the data, is the systems that have relationships between resources that you have and the tags. So you can say these resources, these tags are owned by these resources. Very simple data model, right? That is all stored with a key value pair Cassandra, because that gives you huge availability in terms of reads and writes. And that's something that the tag system itself is becoming very core to a lot of the operations in RightScale. So another interesting example here is the audits, for example. Audits is the systems that receive the audit entries, the information about everything that is happening in your account, and stores these things, which could be fairly beefy. So in that case, you need really, really write availability. When you have an audit and you need to write it, you need to write it. It doesn't work if the audit system is down, right? You need to write it. Now, the audits are obviously require much less read scalability, because you don't really read your audits very often, right? So that's one of the things that Cassandra really shines. Writes are much faster than reads, which is counterintuitive, but it is. And the last example that I have here is these events, which is the recent events that we present you in the dashboard, like the sidebar that says everything that's been happening in the last 10 minutes. So for that, for example, we use Cassandra, and we use this TTL sort of feature that it has. So we write a bunch of stuff to the events Cassandra ring, but everything with a TTL of 10 minutes. So then we can very easily pull that data store and say, give me everything that has happened for the last 10 minutes for this account or for this user. And everything that is there is what you want. Because everything that's been this window of 10 minutes will keep expiring, all these rows that you've added. So Cassandra does that for us. It's a funny way to use it, but it works fairly well. And again, every single row that we have here in Cassandra, like in mySQL, is tagged by an account, because we know that every single piece of data, which account it belongs to. So what does that mean in terms of being in that quadrant over there? Oh, by the way, we use S3 for some archiving, but that's typical, like everybody does it in kind of the same way. Okay, so I won't get into the details on that. So what does it mean to be in that quadrant? Well, that quadrant really is about data that we need to present to the user, so we need to get closer to the user, and supposedly it's tagged by account. So we could horizontally partition that space and have these cookie cutter RightScale subsystems that are assigned to different pieces of data, right? So what does that? So we call these guys clusters, okay? So we have, what does that mean? So It means that RightScale has a big set of accounts. We partition those accounts in some way, and we assign this data to each of these clusters. That way, we can add more clusters. We have more horizontal scale. Okay? The interesting thing is that there are not really dependencies amongst them. So it makes it for very good horizontal scalability. Now remember, there's one, not dependency, but one thing that feeds into this, and that is the global system that it should be kind of here on that side over there. It's still going to have to replicate read-only for all the global data to them. But this global data is not too big. So what do we get with this? Well, one cluster serves n accounts. One account will have only one home. We can actually migrate accounts from one to another because, as we said before, every row is tagged. So if I know that I want to migrate account 10, I can get all the rows for account 10 and stuff them over there. So, okay, so that was from the horizontal scalability in terms of data, but also remember that the first premise that we had in that quadrant was that it was user data, so we wanted to be able to push data close to the user. So if we have this partitioning, we could collocate the clusters according to where the accounts of that cluster want to be. So if I have a lot of users in Japan, I could have, or like in the EU, I could send their accounts to this cluster so that their access is faster, right? That was the initial premise that we have. Good. So that's for that quadrant over there. Now this quadrant over here is about putting the data close to the instances, but also this data is account related. There's no global data, so to speak. Okay? So there were three subsystems that I have as an example in this area. So the first thing that one needs to take a look at this is that, well, can we do the same thing there? Can we horizontally scale these subsystems based on something? And the answer is yes, we can, and we call them islands, right? We horizontally scale these systems based on some criteria, which is not account. Why is it not account? Because what we want to do is that be able to push this to the clouds, close to the instances. So an account may have instances running in any island, right? I can have cloud instances running in 10 clouds if I want to. So I cannot. The partitioning is not by account. The partition has to be by cloud resources. Okay? So that's what we call them. We don't call them clusters, we call them islands because it's a different way to partition the data. Now, what does that mean? It means that if we have these islands, I'm just blowing the lower right corner, we're going to have different islands which have these three services. There's many more, but three representative services. And the key there is that we want to collocate them inside a cloud where the instances that they serve live, right? We want these guys very close to the instance. When this guy comes up and says, I want to route this message to foo, and they're basically using a system that is collocated within the same cloud that they are, right? When we want to start monitoring and getting metrics from certain instances, we don't want the metrics to go from this cloud all the way through the internet to another cloud. It's not necessary, right? So that's the premise behind that. So how do we do that in terms of data? Well, as you see, it's a mix of relational databases and Cassandra again, and some custom stuff. So for example, the gateway systems. The gateway systems are the systems that pull the clouds for existing resources with your credentials, sees what I had before, what it is right now. If there's some changes, I'm sending messages. We transform pulling to the cloud to a stream of events of changes to our core systems. That's just because the clouds do not support an event of changes. That's why we have to do it ourselves. Okay? So they constantly pull and they store things in their master database, and we use master-slave technology for that. But really, the data model that they have is really simple. So we could easily port that into a NoSQL database because everything that we store is very columnar, if you will, or like table separate. We don't do many joins at all. Okay, so the reason we have mySQL there is just we started that way 3 years ago. Okay, but we kept it really simple so that we actually can move to NoSQL if we want to. We do need some atomicity operations, but that usually when you need atomicity operations, you build something on top of NoSQL, like Zookeeper, or maybe you use another mySQL just for locking or something like that. Okay. So the interesting thing is that because it's only a resource cache, we can horizontally scale this very nicely because we can really collocate gateways for each cloud in different places. So a gateway for a cloud polling is completely independent from other gateways polling, right? So there's no relationship. They only know I have these accounts in this cloud and that I'm polling. And I don't care if there's 50 more gateways polling their own accounts. So that's very good from that perspective. From the monitoring, I don't want to spend a lot of time there because there's really not that interesting, but I just had it here as an example of a custom data storage. These monitoring machines constantly get metrics from instances and store them. From a point of view of monitoring, we store them in RRD files, right? So this kind of cyclical, redundant, metric thing. But really, we store them in normal disks, and we use S3 for archiving and backup of these files. But they're really local files. It's very simple, very simplistic, embarrassingly parallel type of scenario. You want more monitoring, getting data, well, you put more nodes, and they'll save locally with backups to S3. Okay, nothing special there, but I just wanted to give you a feel that not everything has to be super technologically advanced. And then last, and the most important part here is the routing. The routing is the key here there. So we use Cassandra, again, because the data adjusts much better to a key value pair type of thing. Cassandra, I don't want to seem that Cassandra only supports this type of scenarios. Cassandra is very powerful from the point of view you have rows that you can add to a table. They call them column families. But a row could be something that is not only like a subset of well-known columns. You could have rows that are super long. And within these long rows, you actually can do searches too. So in some situations, for the tags, for example, we have a row that belongs to an account and a particular resource, and then we have one column within that row that has one tag. So you can say, this particular resource with this URL, what are the tags? So we just read all the rows there. You can also do prefix searching and things like that. So I don't want to make it sound, if you guys are not used to Cassandra, it's quite powerful. So this system over here, the routing system, needs to be really highly available. When somebody wants to route a message to another machine, we need to know where to go and send the message over there. So Cassandra allows you a lot of also replica control. You can say, these particular pieces of data, I want 3 copies. These particular pieces of data, I want 5. Right? It's up to you. And on top of it, an interesting thing that we heavily use in this is the multi-cross-DC replication. So if you've been paying attention, this is the first time that I have a line going across these guys, right? That has the feel of something global, which it kind of is. In this case, the interesting thing is that because of the way that we're laying this thing up, we're separating account access and we're separating cloud access. An instance that belongs to one account needs to be able to know where his home account is, and also he can send a message to an instance for the same account that may be running in another island. So if, I don't know how to explain it here, but if an instance here is from my account and I want to send a message to instance foo, also from my account, instance foo maybe is running in this cloud, right? So I have to know how to get to that. So there's a global component there that a Cassandra replication and multi-data center really helps us. So the way that this works is that every single ring here that you have on each island is it's a full copy of the ring of the other ones. So there's a single global physical ring, but Cassandra understands that these nodes over here have to be a self-contained sub-ring with the same data that this other DC is over there. So we don't have to do anything other than write and read. And Cassandra does the spreading for you. When an instance over here wants to send certain messages to any particular part of, or a better example, from the dashboard, you want to run a script on an instance, right? You're coming from over there, and you somehow have to reach. So there's a system of queues that belong to agents, so you need to know which queue do I send these things. Does that make sense? It's basically, yeah, a system of where are the agents and how do I get to them. Okay, so this is kind of a overall thing of where we are. So we could, from a user perspective, we could partition based on account, and that allows us to really push these things to specific geographies, right, based on when the clients are. And also allows us to push different islands into the different main clouds that we support. Now, I have to say that doesn't mean, the fact that we have islands that we can partition horizontally doesn't mean that we have to have an island for each cloud. We just kind of want to have an island that is close to a certain set of clouds. Obviously, we want to have an island in some cloud that is big enough that has a lot of resources next to it, but we don't have to have an island for every of your private clouds. This is collocated with a cloud, right? What happens if the whole cloud goes down? Nothing, because these instances go down too. So there's nothing to manage, right? So that's an interesting property in here. This could be heavily replicated across data centers within that cloud and everything, but if the whole cloud goes down, you don't need to do anything because there's nothing to manage. Now here, this is a different story. Now this is a heavily, replicated, multi-availability zone, the whole shebang, but if this goes down, the clients still want to access their dashboard, right? They don't go away like the instances go away here. So we have to fix that. So that's where the DR strategy comes in, and it goes like this. What I said. So if that fails, it goes like this. So what we do is to have, we pair clusters, right? So there's two clusters that are going to be sister clusters. And these are is a special relationship amongst them, such that one will be a full replica of the other one all the time, right? So how do we do that? Well, first of all, we're going to have some extra databases in here, right? So one database, the master database of cluster, cluster 1, will have to replicate and have a copy over here, and we have to do the same thing for the other one, right? So they cross-replicate every single relational database that we have across, and for the local rings, for the Cassandra store, we do the same thing. But for the Cassandra store, it's free, because there's some mode of Cassandra that you can say, these nodes, very similar to what you saw on the routing scheme, these nodes belong to data center X, these nodes belong to data center Y, they're really connected to the same physical ring, make sure that they all have a copy of each other. Now the interesting thing here is that for Cassandra, all the clients that are over here, reads and writes are local. And on the clients that are over here, reads and writes are local. So that's very important, right? So then what happens? We have this, and say, whatever this is deployed in some east cloud, the whole thing goes down, right? Doesn't matter that we have copies in all availability zones. So when that thing goes down, basically, the only thing that you have alive is this. So the initial thing that one can think of is, well, let's start launching more hardware at it so that we can start serving the accounts that belong to these guys, right? The first thing you're going to have is that everybody that lost this cloud is going to probably start wanting to launch more resources over there, right? So what we have devised is a way that I say, well, I don't want to necessarily start launching new resources because there may be a shortage. So what I'm going to do instead is that we build a software so you can tell the existing software to say, now you're actually serving this account set and that account set. So now they can access the data that is replicated here and the data that is already replicated here. So suddenly you're serving, say, twice the amount of accounts with the same hardware, but you're already serving it immediately, right? And over time, then, if we can launch more stuff, then we can help this extra load so that it stabilizes until we can DR back to the original one. So this will be the third line of defense from the point of view of having a whole cloud region go down, basically. I think I'm actually done. I just wanted to kind of wrap up really quickly that I hope that shown that we use multiple technologies, mostly mySQL and Cassandra, to achieve all kinds of availability. And also I wanted to point out that we do heavy use of partitioning, horizontal partitioning based on cloud resources at the lower level for the routing, account basically data at the higher level, so we can push data to the users, close to the users. We can push data close to the instances. And we have this cluster pair thing that we're testing out in terms of really big failures of cloud. That's kind of, in a sense, the gist of it. So I think that there's a couple minutes most, but at least that's done and we can leave.